Section: Introduction. In this section, we discuss scaling laws, which have proven to be effective for predicting model performance, such as training loss on held-out data, and for determining the best model size within a given computational budget. Typically, scaling laws estimate the training loss based on the size of the model and the dataset. However, these laws depend on the specific training distribution used to derive them, and we know little about how they vary with different pre-training distributions or how to use them to forecast performance on new test distributions. We take an initial step to explore how scaling laws shift when we alter either the training or testing distribution. To achieve this, we introduce a method called loss-to-loss prediction, which allows us to estimate the loss on one dataset based on the loss from another. This method is beneficial because it enables us to apply a scaling law derived from one dataset to predict scaling for another. We identify three types of loss-to-loss relationships. First, in train-to-train comparisons, we observe a shifted power law relating training losses from models trained on different datasets, which helps us understand how scaling laws differ across datasets. Second, in train-to-test scenarios, we find a similar shifted power law when evaluating a model trained on one dataset against another, although this is less useful for making predictions about new training sets. Third, in test-to-test comparisons, we again see a shifted power law when comparing test losses across models trained on different datasets, though these results are noisier. We also explore practical applications of these relationships. When we have a scaling law fitted on one dataset, we can make predictions about a new dataset with only a few training runs. Specifically, we show that using train-to-train predictions can significantly improve our estimates with just 8 models trained on the new dataset. Additionally, we find that test-to-test predictions can provide better insights than relying solely on new dataset runs. In summary, our main contributions include developing a methodology for loss-to-loss prediction that connects scaling laws across datasets, demonstrating various prediction types across multiple pre-training datasets and downstream tasks, and discussing the implications for understanding scaling laws and transfer learning. We highlight that using data from multiple pre-training datasets can enhance predictions for new datasets compared to fitting independent scaling laws. Section Summary. In this section, we introduce scaling laws as a method for predicting model performance across different datasets and propose a loss-to-loss prediction methodology to translate these scaling laws between training and testing distributions. We observe 3 types of loss relationships: train-to-train, train-to-test, and test-to-test, and demonstrate that leveraging data from multiple pre-training datasets can enhance predictions for new datasets, ultimately contributing to our understanding of scaling laws and transfer learning. Section: Notation. In this section, we focus on understanding how transfer works across different training distributions. We define 2 distributions, which we label as P0 and P1, where P0 serves as the source and P1 as the target. Our aim is to use the loss from P0 to predict the loss on P1. For instance, P0 could be fine web, while P1 might be starcoder or hellaswag. We denote the loss calculated on each distribution as L_I, averaged per token. If P1 involves a multiple-choice task, we define L1 as the loss for the correct answer when the question is presented in a close format. For a given pre-training distribution P_I, we represent a model with n parameters trained on D tokens from P_I as _I_n, D. Our results compare the losses L0 and L1 for models _0, n, d, and _1, n, d, across various choices of P0, P1, n, and d when we refer to a scaling law fit from our previous work on distribution P_I. We add a subscript to the relevant parameters, such as E_0 for the irreducible entropy on PO. To support our analysis, we pre-train models of different sizes and flop budgets on 6 datasets: Fine Web, Fine Web Edu, Proof Pile 2, Slim Pajama, Smol LM Corpus, and Starcoder V1. We utilize Olmo for training and adhere to specific hyperparameter settings, which are detailed in the appendix. We implement a linear warm-up and cosine decay schedule for each run, reporting only the final performance. Our flop budgets range from 2E17 to 4.84 times 10 to the 19, with model sizes from 20 million to 1.7 billion parameters. The best model at the largest flop budget is approximately 750 million parameters, varying by dataset. Overall, we have a total of 528 models, averaging 88 per dataset. For our extrapolation experiments, we train 6 larger models, one for each dataset, each with a flop budget of 1E21 and a size of 3.3 billion. Next, we present the relationships between losses, which are central to our findings. We explore train-to-train, train-to-test, and test-to-test relationships. Our first key observation is a consistent scaling relationship between training losses across datasets. We find that by fitting just 2 parameters, k and kappa, we can effectively capture and extend the scaling relationship between pairs of training losses. This comparison involves different losses in models, but we ensure that the models are paired based on having the same number of parameters and tokens trained. We note that E_0 and E_1 represent the irreducible errors from independent scaling law fits on P0 and P1, respectively. Since we are fitting a slope and exponent, each curve appears linear on a shifted log-log scale. However, due to plotting 6 curves with varying E_1 values, we choose a linear scale for clarity. Regarding scaling law parameterization, we observe that neither the Chinchilla nor Kaplan equations provide a valid mapping for the translations we define. Therefore, we adopt a slightly different functional form that allows for valid scaling law translations, essentially modifying the Kaplan equation by adding an entropy term. We acknowledge that while this approach yields valid translations, we are open to exploring other formulations. We believe it is an intriguing question to determine the most accurate formulation for scaling laws. Under our parameterization, we establish relationships between the scaling law parameters for L1 and L0, demonstrating how our translation connects one valid scaling law to another. Section Summary. In this section, we define 2 distributions, P_0 as the source and P_1 as the target, to study transfer learning by predicting loss on P_1 based on loss from P_0. We observe a consistent scaling relationship between training losses across datasets, allowing us to extrapolate these relationships using a modified scaling law parameterization that incorporates an entropy term. Section: Compute optimal models. In this section, we compute optimal models. We find that under the parameterization for translating between losses, the size of the compute optimal remains unchanged. Specifically, the optimal model size for a given computational budget can be expressed as a fraction of the budget raised to a power, where this power depends on the scaling of the data. This means that for any given computational budget, the optimal model size stays the same across different data distributions where this relationship applies. While this conclusion seems strong, it aligns with common practices where practitioners often train on significantly more tokens than the number of parameters in their models. However, if we change the model architecture or training algorithm, this invariance may no longer hold. We find that this invariance roughly holds across the 6 datasets we tested, which vary widely, but it may not apply to all dataset pairs. Next, we note that the exponent values we observe are generally close to 1. If the exponent equals 1 for a pair of datasets, it indicates they have the same scaling behavior. Across all dataset pairs, the minimum exponent is 0.88 and the maximum is 1.13, which occur between specific datasets depending on the prediction direction. Although these values are close to 1, they are different enough that trying to fit a linear model would lead to poor predictions. In contrast, the constant we observe tends to be further from 1, with the largest differences appearing between certain datasets. This suggests that the differences in scaling returns between datasets are evident in the scaling law's numerators. It is also noteworthy that we can fit a single constant that modifies both components of the scaling law. In summary, our findings have several implications. Since the constants are not close to 1, different datasets can lead to significantly different reductions in loss. However, under our translations, the optimal model size remains unchanged regardless of the training distribution. Our formulation of the scaling law is the only one compatible with the relationships we established. If we used a different formulation, the resulting scaling law would not maintain the same functional form. We then extend our analysis to translating training loss to test loss for the same model under a different distribution. We hypothesize a specific relationship for this translation. We define a term representing the irreducible error for the optimal function with infinite model and data sizes, which we estimate by fitting a scaling law to the training loss data. We evaluate multiple models trained on the initial dataset and assess their performance on an out-of-distribution test set. This allows us to fit a scaling law and determine the irreducible error. Our results show predictions for validation sets from the pre-training distributions and translate from training to downstream test sets. We evaluate downstream tasks using cross-entropy loss on the correct answers. We observe that many transfer curves are close to linear, but there are exceptions when transferring from datasets with little code to those that are entirely code. These exceptions indicate diminishing returns in performance, suggesting that training well on English does not significantly improve performance on code tasks. Additionally, we find that the asymptotic transfer performance on test sets can be worse than training directly on those datasets. This highlights the importance of including diverse training data that encompasses the test domains we care about. In downstream tasks, we observe greater curvature in the performance curves, often showing increasing returns to improvements in training loss. We hypothesize that this occurs because the target tasks may only be effectively addressed by larger models or later in training. Despite these increasing returns, we see smooth improvements in loss rather than accuracy, which we discuss further in a dedicated section. Section Summary. In this section, we demonstrate that the optimal model size remains invariant across different data distributions for a given flop budget, as long as the underlying scaling laws hold. We also explore the implications of this invariance on train-to-test predictions, revealing that while different datasets can yield varying returns to scale, broader training data is crucial for optimal performance on specific test domains. Section: Implications. In this section, we explore the implications of train-to-test prediction. Our findings highlight the significance of data selection, as predictions from pre-training datasets show that even when we extend the curves to their limits, the loss on transfer datasets does not approach the lowest possible error for the task. This means that the error from our first dataset does not get close to the irreducible error. We observe that downstream loss is predictable and does not reveal unexpected properties. By tracking this downstream loss, we can smoothly estimate performance on relevant tasks. We notice that some tasks have a convex relationship with pre-training loss, where reducing pre-training loss yields smaller benefits, while others have a concave relationship, where reductions lead to greater benefits. Typically, downstream tasks exhibit concave relationships. Next, we discuss test-to-test prediction, which combines the previous two concepts. This involves three data distributions: the initial training distribution, the target training distribution, and the test distribution used to measure loss. Similar to train-to-train predictions, we compare losses across different models, but now we focus on test loss. This approach generalizes train-to-train predictions. We pair models based on the same number of parameters and training tokens. Our results, shown in a figure, indicate that we can extrapolate well to models trained with significantly more computational resources than those used to fit the curves. The fits are particularly strong for one dataset, HelloSwag, although other datasets tend to be noisier, which affects our measurements. We then propose a general loss-to-loss prediction that encompasses the three types we discussed. This framework allows us to translate losses between different distributions based on models trained on various datasets. We can predict test loss from training loss, which tends to have lower variance. We also highlight how loss-to-loss prediction can outperform independent scaling laws. For instance, if we have already established a scaling law on one dataset and want to know the implications for a new dataset, we can use loss-to-loss prediction instead of fitting a new scaling law independently. This method allows us to make accurate predictions with fewer model runs on the new data by leveraging existing information. In the context of translating a scaling law, we consider two pre-training distributions. After fitting a scaling law on the first distribution with many small models, we fit a few models on a new distribution and aim to derive a scaling law for it. We compare our approach of translating the scaling law using train-to-train predictions with a baseline of independent scaling laws. Our results demonstrate that using train-to-train predictions significantly improves the efficiency of fitting a new scaling law, even with a limited number of models on the new dataset. This shows that utilizing existing models can lead to better scaling law fits on new distributions. Section Summary. In this section, we discuss the implications of train-to-test and test-to-test predictions, highlighting the importance of data selection and the predictable nature of downstream loss, which can be used to extrapolate performance across tasks. We also demonstrate that loss-to-loss prediction can significantly improve scaling law fits on new datasets by leveraging existing models, outperforming independent scaling laws even with limited data. Section: Predicting test loss on a large model. In this section, we explore how to predict test loss for a large model. We start with two pre-training distributions, which we label as P0 and P1. We have already trained 4 small models and 1 large model, which has 3.3 billion parameters and requires 1 quintillion floating point operations, on the distribution PO. Now, we introduce a new dataset, P1, and train 8 small models with different budgets on it. Our goal is to predict the performance of a large model trained on P1. We will examine several approaches, as shown in our figure. First, we use a method we call general train-to-test prediction, where we create a curve that relates training losses from the 8 small models. Specifically, we predict the loss of the large model on P1 based on its loss on PO. Next, we apply test-to-test prediction, which involves fitting a curve using the test losses of the small models to predict the large model's loss on P1 from its loss on PO. For our baselines, we first consider flops to test, where we fit a curve from the number of floating point operations to test loss without using information from PO. Since our models are close to the optimal size for their flop budget, this approach seems reasonable. Another baseline is independent scaling law, where we fit a scaling law to the small models on P1 and make predictions based on that. Lastly, we have the identity baseline, which simply assumes that the test loss on P1 will be the same as on PO. We report our findings in terms of relative error, which measures the difference between our predicted and actual test losses across various test sets. Our results indicate that the loss-to-loss methods generally perform the best, as they utilize additional information, particularly the loss of the large model on PO. We observe that train-to-test predictions often outperform test-to-test predictions, especially on noisier evaluation datasets, because using a more stable variable for predictions reduces variance. In our discussion, we summarize our key findings, limitations, and future research directions. We conclude that loss-to-loss fits with shifted power laws effectively describe trends across different pre-training datasets and tasks, allowing for reliable extrapolation. These predictions are scientifically valuable as they shed light on how training data influences model performance and scaling. However, we acknowledge some limitations. Our fits depend on estimating complex quantities, which can be challenging, and we suspect that inaccuracies in these estimates may lead to failures in our predictions. Additionally, we note that some of our fits exhibit noisy trends, particularly at high loss levels, raising questions about the validity of our power law assumptions. Our testing has been limited to a small set of downstream tasks, focusing on multiple choice tasks rather than generative ones, which may affect the generalizability of our results. We also recognize the need to examine the robustness of our findings with different hyperparameters, such as sequence length, batch size, and learning rate. Section Summary. In this section, we predict the test loss of a large model trained on a new dataset by leveraging insights from smaller models trained on both the original and new datasets, finding that loss-to-loss methods generally yield the best predictions. We also discuss the effectiveness and limitations of our approaches, emphasizing the need for careful estimation of scaling laws and the potential for future work in data selection and robustness testing. Section: Future Work. In this section, we explore future work directions. One promising area is to delve deeper into the loss-to-loss relationships to enhance data mixing and filtering. Once we achieve reliable predictions, we can better decide which data to use for training. We might leverage the scaling laws we've derived alongside recent findings that connect scaling laws with data mixtures. We aim to develop a clearer theoretical understanding of why the loss-to-loss relationships appear so consistent by examining simplified models. In our appendix, we try to link existing theoretical literature to our findings and demonstrate that a basic version of train-to-train transfer can be seen in certain linear models we've studied. We also seek a deeper theoretical insight into train-to-test transfer and aspire to create a more comprehensive model that captures the full range of phenomena we observe. Our results reveal unexpected connections between seemingly unrelated datasets, allowing us to predict performance on code data using non-code data and vice versa. We would like to gain a clearer understanding of the mechanisms behind this. It's possible that all models converge on features that share similar high-level distributional traits, such as comparable patterns in eigenvalue decay of the covariance. Alternatively, the data might be more similar than we realize, with enough English present in code and vice versa, making losses predictive. There may also be specific shared structures that arise, particularly in context learning.